Welcome back, everyone. In this lecture, we'll be discussing null hypothesis significance testing and some related concepts. We'll begin with an introduction to null hypothesis significance testing. We'll then discuss the idea of null versus alternative populations, two-tailed versus one-tailed tests, alpha values and critical values, p-values, and test statistics. In our last video, we learned that statistics allow us to draw conclusions about a population based on a sample, using the central limit theorem. Drawing conclusions about a population based on a sample, however, involves error, specifically sampling error. Statistics allows us to account for this error and attempt to reduce it by applying concepts like degrees of freedom and the sampling distribution. So let's talk about the questions that we can answer with statistics. And specifically, what does it mean to draw conclusions from samples about a population? It means that we want to know if our sample came from the population we're comparing it to. So let's consider a research question that we'll call question 1. Are UCSB students happy with online learning? This is a descriptive question, and questions like this generally are not the main focus in statistics. So let's look at a more typical question. So question 2 is, are UCSB students happier with online learning than other college students? In statistics, we usually want to compare distributions to each other to determine if they're significantly different or not. So notice that difference here. In question 1, we're just asking whether or not the UCSB students are happy. In question 2, we're making a comparison of happiness between UCSB students and college students in general. The process that we follow to answer these questions is known as null hypothesis significance testing, abbreviated as NHST. As I mentioned before, we want to know if our sample came from the population we're comparing it to. If it has the same mean as the population, this suggests that it most likely came from this population. However, if the sample mean is different from the population mean, it probably came from a different population. But we run into a problem with sampling error, because sampling error means that there will always be a difference between the sample mean and the population mean. What null hypothesis significance testing does for us is allows us to determine whether the difference is big enough to make it likely that the sample came from another population and was not just due to sampling error. Let's walk through null hypothesis significance testing step by step. Step 1 is to state the null and the alternative hypotheses. Step 2 is to establish criteria to reject, or fail to reject, the null hypothesis. Step 3 is to calculate the test statistic based on the sample data. Step 4 is to make a decision based on the test statistic, to either reject the null hypothesis or fail to reject the null hypothesis. So this is a very quick overview, and we will spend the rest of this video breaking down each of these steps in a lot more detail. Let's start with step 1, null and alternative hypotheses. So recall, our research question is, are UCSB students happier with online learning than other college students? Based on this research question, our null hypothesis is going to be that UCSB students' happiness with online learning is the same as other college students. Once we've identified our null hypothesis, our alternative hypothesis will simply be the exact opposite of the null. So in this case, our alternative hypothesis is that UCSB students' happiness with online learning is different than that of other college students. Notice that this is a non-directional alternative hypothesis. We didn't specify whether their happiness was higher or lower, we just said that it would be different. We'll return to this idea in a couple slides. Notice also that the alternative hypothesis contains all logical probabilities not covered by the null hypothesis. And sorry, I forgot to change that bit on the slide. And critically, because the alternative hypothesis contains all logical probabilities not covered by the alternative hypothesis, either the null hypothesis or the alternative hypothesis must be true. There's no way that we could end up in a situation where both are true or where neither are true. And that's important. Let's talk a little bit about the purpose of the null hypothesis. The null hypothesis states what the results would be if there was no systematic variability in the world. Under the null hypothesis, any difference between the sample mean and the population mean is due solely to sampling error, in other words, chance. Now, this is not just pessimism. The null hypothesis is incredibly useful because it puts all tests on an equal playing field. If we start with this baseline assumption that there is no systematic variance, we can calculate the probability of a statistic occurring by chance alone. This is possible because we have a lot of information about the sampling distribution when there is no systematic variance. It wouldn't be possible to map out the sampling distribution for every possible study. And this means that if the probability of the observed statistic occurring due to chance is extremely small, it suggests that there is in fact systematic variability at work. We'll be returning to this theme many times as we go through this lecture. So let's talk in a little bit more detail about how we write out the null and the alternative hypotheses. Let's assume that the population mean for all college students' happiness with online learning is a 3.2 out of 5. This means that our null hypothesis, which we can abbreviate H0, is that mu, the population mean, is 3.2. And specifically, this mu refers to the mean of the population that our sample came from. In other words, our null hypothesis is that the mean of the population our sample came from is the same as the mean of the college students' population. This is known as the null population. Our alternative hypothesis, abbreviated H1, is then simply that mu is not equal to 3.2. Notice here, again, that it's non-directional. It's not saying that it's greater than 3.2 or less than 3.2, just that it's not equal to 3.2. This alternative hypothesis implies that the mean of the population that UCSB students come from is not the same as the mean of the college students' population, the null population. In other words, that UCSB students belong to a population different from the population that other college students belong to, as far as their happiness ratings for online learning go. And one last important point here. Null and alternative hypotheses are always represented in terms of parameters, not statistics, because the hypotheses are about populations, not samples. This means that your hypotheses should always be written with Greek letters, not English letters. Let's talk briefly about directional alternative hypotheses. First, if our alternative hypothesis is non-directional, it's known as a two-tailed hypothesis. So in this case, our alternative hypothesis would be that UCSB students come from a population that is either higher or lower than the null population of other college students. We would express that as follows. The null is that mu is equal to 3.2, and the alternative is that mu is not equal to 3.2, as we saw in the last slide. Two-tailed tests are by far the most commonly used type of test in psychology. A directional, or one-tailed alternative hypothesis would be something like this. UCSB students come from a population that is higher than the null population of other college students. Or, alternately, UCSB students come from a population that is lower than the null population of other college students. So in this case, if we go with the alternative that it's higher, our null would be that mu is equal to or less than 3.2, and our alternative hypothesis would be that mu is greater than 3.2. Notice that, once again, the null and the alternative completely exhaust the logical possibilities. One of them, and exactly one of them, must be true. The decision about whether to use a one-tailed test, and the decision of which direction for it to go in, is usually based on theory or previous findings. One shortcoming of one-tailed tests is that they cannot detect differences in the opposite of the predicted direction. And we'll talk about this more in a couple slides. Let's move on to step 2 of null hypothesis significance testing, establishing the criteria to reject the null hypothesis, H0. So here, just to recap, are our null and alternative hypothesis. Our null hypothesis is that UCSB students' happiness with online learning is the same as that of other college students. Our alternative hypothesis is that UCSB students' happiness with online learning is different than that of other college students. Remember, the null hypothesis is the baseline assumption. So to support the alternative hypothesis, we must reject the null hypothesis. In other words, we must demonstrate that the difference between the sample and the population is not just due to chance, in other words, sampling error. Now, of course, the larger the difference, the less likely it is that it's due to chance. And, conveniently, we can quantify this chance thanks to the central limit theorem. We know what the distribution of sample statistics, for example, sample means, should look like if the null is true. and it's represented here by this bell curve on the right. This is the sampling distribution of the null population. By definition, its mean is mu, the population mean, and its standard deviation we can calculate using the formula for standard error. So again, this is just a recapitulation of the central limit theorem. Now, because we know what this distribution of statistics will look like if the null is true, we can calculate how likely a given statistic, for example, a given sample mean, is to occur if the null hypothesis is true. In other words, how likely would we be to get that sample mean from the sampling distribution of the null population? So let's say that our sample mean falls here. So notice that's greater than the population average, but it's still within sort of the central body of the distribution. So it's not incredibly likely, but it's not unlikely either. Now say our sample statistic fell out here. Well, that's less likely to occur if the null hypothesis is true. And what if our sample statistic is way out here? That seems extremely unlikely to occur if the null is true. The key idea here is that the lower the likelihood of a given statistic occurring if the null is true, the more likely that that sample is not from the null population, which suggests that we should reject the null hypothesis. But how much does the sample mean need to deviate from the population mean in order for us to reject the null? The decision to reject or fail to reject a null hypothesis involves a risk of being wrong. If we decide how big of a risk we're willing to take, we can pick an appropriate cutoff point. And we do this using something called the alpha level. The alpha level represents the proportion of the sampling distribution that we consider to be sufficiently extreme to reject the null. It also corresponds to our risk of incorrectly rejecting the null hypothesis, otherwise known as a type 1 error. So here we have our sampling distribution of the null population, just like we saw on the last slide. This line here represents the mean of this distribution, which again is the mean of the population. The part of this distribution that's shaded in red is known as the critical region. That's the proportion of the distribution that we consider to be sufficiently extreme to reject the null hypothesis. The amount of this curve that's colored red adds up to alpha. In this case, because there's a little bit on the upper and lower end of the distribution, each of those areas is half of our total alpha value. This blue area in the middle is then equal to 1 minus alpha. It's everything left over. So let's say our alpha was 0.1. That would mean that 10% of the area under this curve, 10% of the distribution, would be the critical region, the region in red, and the blue area would be the remaining 90% of the distribution of the area under the curve. So how do we figure out if an observed statistic falls into the critical region? The answer is that we identify the critical values that separate the critical region from the rest of the distribution, represented by these little vertical red lines, as you see on the right. If the observed statistic exceeds the critical value, represented by that black arrow, then it's unlikely to be due to chance, and we can reject the null hypothesis. So, some key points here. The critical value is the dividing line between the critical region and the rest of the distribution. Where it lands depends on the alpha that we pick. We'll talk about exactly how to determine critical values in our next lecture. So, how do we pick an alpha level? As I mentioned before, deciding to reject or fail to reject a null hypothesis involves a risk of being wrong. Incorrectly rejecting a null hypothesis, in other words, saying that something was due to systematic variance when in fact it was just due to random chance, is known as a type 1 error. On the flip side, incorrectly failing to reject the null hypothesis, in other words, thinking that something was just due to unsystematic variability when in fact there was systematic variability at work, is known as a type 2 error. To deal with this issue, we define a chance of being wrong that we're okay with and base our critical value on that. Traditionally, researchers in psychology use an alpha level of 0.05 as a common rule of thumb. When we reject a null hypothesis at an alpha level of 0.05, we accept a 5% chance that we're wrong. In other words, there's a 5% chance that the sample we decided comes from another population actually came from the null population. If we use a smaller value of alpha, we impose a stricter criteria, and have less risk of a type 1 error. So, if our alpha is 0.01, it means that we're only accepting a 1% chance of being wrong. But of course, this also increases the chance of type 2 error. So we're less likely to incorrectly think there's an effect when it's actually just noise, but we're more likely to incorrectly think that it's just noise when there's actually an effect. Let's move on to step 3 of null hypothesis significance testing, calculating the test statistic. The exact test statistic you calculate depends on the test that you run. If you run a z-test, you get a z-statistic. If you run a t-test, you get a t-statistic. No real surprises there. You will also calculate an associated p-value. Test statistics are measured against a critical value, and p-values are measured against your alpha value. Let's talk about this in a little bit more detail. The alpha tells us the amount of error associated with the critical value. If the test statistic is greater than the critical value and the null is rejected, there is a chance, equal to alpha, that this sample actually came from the null population. For example, if UCSB students' scores differed from the mean of other college students' scores greater than the critical value, and we decided that UCSB students' scores came from a population other than that of the other college students, at an alpha level of 0.05, there would be a 5% chance that UCSB students' scores came from the population of other college students. In other words, that we'd made a type 1 error. The p-value tells us the amount of error associated with the test statistic. In other words, the chance that the calculated difference between the sample mean and the population mean is only due to sampling error. We'll cover how to calculate test statistics in the next lecture, and in basically every lecture thereafter. For now, let's talk about how we make a decision. There are two approaches we can take here. One is to compare the p-value that we calculate to our alpha. If p is less than alpha, we reject the null hypothesis, and if p is equal to or greater than alpha, we fail to reject the null. Another approach is to compare the test statistic to the critical value. If the absolute value of the test statistic is greater than the absolute value of the critical value, we reject the null, as shown by the vertical arrow you see here. So here, we have a test statistic that falls beyond our critical value. In this case, I decided that it would be 4. Thus, it falls in our critical region, and we reject the null. On the flip side, if the test statistic is less than or equal to the absolute value of the critical value, as represented by this second arrow, notice that it falls in the blue area of the distribution, we fail to reject the null. Our next lecture will walk through this process in a lot more detail. One thing I'll note is that both approaches will always lead to the same conclusion, so you can use whichever one is easier based on what values you've calculated. Recall from a few slides back that hypotheses and tests can either be one- or two-tailed. Here we can see why. In a two-tailed test, we have two critical regions, one at the positive end of the distribution and one at the negative end. We also have two critical values. One defines the lower bound of the critical region at the positive end of the distribution, and the other defines the upper bound of the critical region at the negative end of the distribution. So a sample statistic can fall in the critical region if it's greater than the critical value on the positive end of the distribution, or if it's less than the critical value at the negative end of the distribution. This means that with a two-tailed test, we can reject the null if the statistic is substantially higher or lower than expected under the null hypothesis. For a one-tailed test, however, we only have one critical region at either the positive or the negative end of the distribution. Here, it's at the positive end. And there's only one critical value. Importantly, the critical value for a one-tailed test at a given alpha level will always be smaller, in other words, closer to 0, than the critical value for a two-tailed test with the same alpha level. This is because alpha defines the proportion of the sampling distribution that we consider to be the critical region. So if alpha equals 0.05, then 5% of the distribution is considered the critical region. In a two-tailed test, the critical region is split between the two tails, 2.5% at the upper end and 2.5% at the lower end. This means that a statistic might exceed the critical value in a one-tailed test, but not in a two-tailed test. And that means that one-tailed tests are more sensitive to effects in the predicted direction, since the critical value is lower and thus it's an easier threshold to pass. However, there's a trade-off. which is that one-tailed tests cannot detect effects that are in the opposite direction. So if we run a one-tailed test to see if UCSB students are happier with online learning than other college students, we would not be able to tell if they were substantially less happy, as indicated by this arrow here on the left. We would just be able to tell that they weren't happier, but we couldn't make a distinction between them being as happy as other college students and them being less happy than other college students. So we've covered a lot of ground in this lecture, and I want to take a moment to tie all of this back in to the big idea of null hypothesis significance testing. We want to know whether the effects and the differences we observe are due to unsystematic variability, in other words, chance alone, or due to systematic variability, variability due to the factors that we're studying. Statistics always slightly differ from parameters due to sampling error. However, thanks to calculus and the central limit theorem, we know how sample statistics should be distributed if the null hypothesis is true. And that means we can calculate the probability, represented by the p-value, of any given sample statistic occurring if the null is true. If p is sufficiently small, then it's unlikely that we'd observe the statistic that we did if the null was true, and that can lead us to conclude that the null is not true. We set our alpha level to determine what counts as sufficiently small. This also corresponds to a critical value. If the statistic is greater than the critical value, it's unlikely to occur if the null is true. So that's the big picture. In our next lecture, we'll walk through some more concrete examples.